Sections 4.2 and 4.3 in a way are like one gigantic section in the book, but they are broken up, so I'll make the videos broken up too, since the homework assignments therefore would also be broken up. So 4.2 mostly is about division, although there is this intermediate value thing here at the very beginning. So this idea up here that if f is continuous and f of a and f of b have opposite signs, so meaning that one's negative and one's positive, then f has at least one real zero between a and b. Sure, think about it graphically. F of a and f of b having opposite signs would mean that one is below the x-axis and the other one's above it. So therefore, if it's a polynomial and it's continuous everywhere, those points have to connect together somehow, and that would mean that whatever connects them together, whatever the function is, it's got to cross the x-axis. Or if it didn't cross the x-axis, it wouldn't be continuous. So it's got to happen. And that's basically all that that's saying. It looks fancier without the graph, but that's basically the idea. I think that's easier to think about graphically. So for these two examples, to show that this f up here has a real zero between -1 and 0, or to show that this one has a real zero between 1 and 2, really all you would have to show is, like for example number 1, if you can just show that f of -1 and f of 0 have opposite signs, that's all that you need. So all I really did here was I just evaluated them, and f of -1 works out to be -4. F of 0 works out to be 7. Those have opposite signs, right? -4 is a negative number, 7 is a positive number. So therefore, there must be a 0 of the function between -1 and 0. And then the same thing happens down here. F of 1 is -9. F of 2 is 23. Those have got opposite signs, right? First one's negative, second one's positive. So therefore, there's got to be a 0 in between them. So between 1 and 2. The next thing is how to divide a polynomial by a binomial. There's a lot of this in this section. It's not all with long division though. So long division is one way of doing it, but there's another way of doing it that we'll get to in a few minutes, I guess. So the way that you have to set this up is you've got to have the dividend and the divisor to both be written with the exponents in descending order. Otherwise, this is a complete mess. So usually they're set up that way anyhow. Right? Usually that's the way that you would write them. Right? Usually you write x squared plus 2x plus 3, not 3 plus 2x plus x squared, but they do have to be written in descending order, or this is a nightmare. The other thing is if you have terms with a 0 coefficient, so like ones that are missing, you've got to include those. So like I've got here, like that function in example 2 referencing this one up here, this doesn't have an x cubed term, right? It's got an x to the fourth, an x squared, an x, and then a constant. But if you were going to do some division involving that function up there in example 2, you'd have to rewrite the 3x to the fourth minus x squared minus 10x minus 1 like this, where then you write in the x cubed term just with a coefficient of 0. Otherwise, all your powers get off if you don't do that. So that's another thing, and that's the one that's easy to forget. So when we go through the examples, when you have to add those in, I wrote them in red just to make them stick out a little bit. And that's why, because it's really, really easy to forget to do that. So then what you end up with at the very end when you do your division as far as like what degree polynomial do you get, the quotient, its degree should be the degree of your dividend minus the degree of the divisor. So if you're just dividing by a polynomial of degree 1, so like x plus some number, x minus some number, then the degree of the quotient should be 1 less than the degree of the dividend. But then like if you divided something that started with like an x to the fifth by something that started with an x cubed, then you'd end up with a quotient that started with an x squared. So that'll eventually happen too. First example, this is actually a thing that would be way easier if I had a real board to do this on, but I guess we'll do what we can here. So if we're going to divide 3x cubed plus 10x squared plus 9x plus 2 by x plus 2, so there's our dividend, the 3x cubed plus 10x squared plus 9x plus 2, the divisor is x plus 2. So basically how this works is you kind of just look at the leading terms and you say, I need to figure out what to multiply x by in order to get 3x cubed. And the thing that you need to multiply x by to get 3x cubed is 3x squared. So 3x squared times x gives you 3x cubed, and then 3x squared times 2 would give you that 6x squared. And then just like with regular long division, then you have to subtract that line out. So 3x cubed minus 3x cubed, that's 0x cubed. And then 10x squared minus 6x squared gives you that 4x squared. So you've got the 4x squared, and then you bring down the next term, kind of like how you bring down the next digit in conventional long division of two numbers. So you bring down that 9x, and then you say, okay, I need to figure out what to multiply by x in order to get 4x squared. Okay, well that's 4x, right? 4x times x will give you 4x squared. So I put the 4x up here, and 4x times x gives you 4x squared, but then 4x times 2 would give you 8x. And then you subtract that line, so 4x squared minus 4x squared, that's 0x squared. And then 9x minus 8x is just 1x, or x. Then you bring down the 2, so x plus 2. All right, well we need to figure out what we multiply x by in order to get x. Well, that's just 1. So 1 times x would give you x, 1 times 2 would give you 2. And so then you have to subtract off that second x plus 2, and you get 0. So that means you have a remainder of 0 at the end. And so then your answer, well, it's the quotient up here. It's 3x squared plus 4x plus 1. In the second example, this is one where we have to be careful because the dividend doesn't have an x term. So you've got to rewrite this as x cubed minus 3x squared plus 0x minus 16. So notice how I've got it here, and I made the 0x red, so it jumps out a little bit. But you've got to do that, otherwise what you get is going to be a little messed up. But then after that, you kind of do what we did last time. So you say, okay, I need to figure out what to multiply x by to get x cubed. Well, that should be x squared, right? X squared times x is x cubed. So x squared times x will give you x cubed. X squared times 4 would give you 4x squared. So then you get x cubed minus 4x squared. We've got to subtract that line off. So x cubed minus x cubed, 0. And then minus 3x squared minus a negative 4x squared, same thing as minus 3x squared plus 4x squared. You would get 1x squared, just x squared, right? And then we're going to bring down the next term, which is 0x. And then we have to figure out, what do you multiply x by to get x squared? Another x. So that's this x up here. So x times x would give you x squared, and then x times 4 would give you 4x, so x squared minus 4x. Subtract that off, you'll end up with a 4x because of 0x minus a negative 4x. So you just get 4x there. Bring down the minus 16, and then what do you multiply x by to get 4x? 4. So 4 times x will give you 4x, then 4 times 4 will give you 16. So 4x minus 16, you subtract that off, you get a remainder of 0 again, and the answer is just what's up on top for our quotient, x squared plus x plus 4. And at some point, we had to have one where we didn't get a remainder of 0. So if you look at our dividend, we don't need to add in any terms with a coefficient of 0. We get an x cubed, x squared, x constant. So we can just go right to it. And then you say, all right, well, 2x squared times x will give you the 2x cubed. So 2x squared times x is 2x cubed. 2x squared times 3 is 6x squared. You subtract that off, you're going to be left with 10x squared because of the 4 minus a minus 6 right there. And then you bring down the next term, the minus 5x. You say, all right, well, then we need 10x next because 10x times x would give you 10x squared. So we need that, and then 10x times 3 is 30x. So 10x squared minus 10x squared, that'll be 0x squared. And then minus 5x plus 30x is 25x. And then we need a 25 because 25 times x will be 25x. And then 25 times 3 is 75. So when we subtract, we won't have any x term left, but then 3 minus negative 75 is 78. So this time we don't get a remainder of 0. So how do you write that as an answer? That's the important question. Well, we're going to have our quotient up on the top, the 2x squared plus 10x plus 25, and then that's how you write the remainder. So the remainder that you end up with, that's 78 divided by the divisor. So it's basically what you would do with long division if you had a remainder. It just looks different because now you've got this polynomial that you're dividing by, but it's the same concept. You end up with that last term where it's remainder over divisor, which you really only need if your remainder isn't 0. Right? If your remainder is 0, it would just be 0 over the divisor, so typically you don't write that in. But that's what it should look like if you've got a non-zero remainder. The other thing here is for that function in example 3, what's f of 3? Well, f of 3, if you substitute in and simplify it, eventually you get 78, which is the remainder. Well, we had divided by, if I scroll up for a second, we were dividing by x minus 3. Okay, so then you look at this theorem down here. If you divide some polynomial by x minus k, the remainder is equal to f of k. So specifically here, we were dividing by x minus 3. The remainder ends up being the same thing as f of 3. That always works, and every once in a while, that's a helpful thing. Sometimes that's a way where you can figure out if the number that you're looking at is a zero function. Maybe that's a faster way of doing it. So that is always true. And that also plays into the next example. Example 4 is another one where we're not going to get a zero remainder. If we're going to divide x cubed minus 7x squared minus 4x minus 3 by x plus 1, we're doing the same stuff, right? We need to figure out what do we need to multiply x by to get x cubed. Well, it would be x squared. So x squared times x is x cubed. X squared times 1 is x squared. Subtract off that line, you'll get minus 8x squared left over. Bring down the next term, the minus 4x. And then what do we need to multiply x by to get negative 8x squared? Well, we need a negative 8x. So minus 8x, or negative 8x right there, times x would be negative 8x squared. And then negative 8x times 1 is negative 8x. Subtract off that line, you'd end up with 4x because you have the minus 4x plus 8x, right? Minus the negative 8x. And you bring down the minus 3. And then you need to multiply x by 4 to get 4x, and that's what this is here. But then 4 times 1 would be 4. You subtract that line off, you get negative 3 minus 4, which is negative 7. So we've got a non-zero remainder. So the answer over here, it's got the x squared minus 8x plus 4, but then minus 7 over x plus 1. And this is a minus right here just from the fact that this is a negative 7. I guess you could write it as plus negative 7 over x plus 1. That would also be correct. But I think this is the more conventional way of writing it. And this is one with a non-zero remainder. So just to kind of add this in, you don't need it to solve the problem, which is why I've got it enclosed in that cloud shape. But f of negative 1, right, which would be the root of x plus 1, if you simplify that, you get negative 7. You get that remainder. So there's that remainder theorem working again right there. The next thing is the idea of synthetic division, which is similar to what you would get with long division. You end up with the same answer, but the way that you do it looks substantially different. Basically, it's condensed. It's much smaller. Like on the page, it's a lot smaller. And if there's an advantage to doing it, it's that once you're comfortable with it, it's kind of fast. So that's the whole reason for doing it, is that you can speed it up. Although synthetic division only really works when the divisor is a polynomial of degree 1 and with leading coefficient of 1. So it's very specific. So it's got to be that you're dividing by x minus 2 or x plus 6 or x minus 3 or something like that. So how do you do it? Well, you write the dividend only with coefficients, and I'm going to kind of do it by pointing stuff out in this first example at the same time, because I think this is much easier to see with actual numbers. So writing the dividend with coefficients only, that's this row right here where I've got the 3, the 10, the 9, and the 2, because those are the coefficients of that polynomial right there. The next thing is you replace the divisor x minus c with its root c. So we're supposed to be dividing by x plus 2. So notice over here I've got a minus 2. This is replacing the divisor with its root. Right? The root of x plus 2 is just negative 2. Then you bring down the leading coefficient. So this 3, that's why I've got this down arrow, that 3 just drops down here. Then what you do is you multiply c, the negative 2, by the value that you just brought down, and you write that underneath the next coefficient. So negative 2 times 3 gives you that negative 6. So this arrow is supposed to signify that you use that 3 to get there, right? It's negative 2 times 3 gives you that negative 6. Then you add down that column, so 10 plus negative 6 is 4. And then you do what we just did, so you multiply that by this root of the divisor. So negative 2 times 4 is negative 8. Then you add down the column, you get 1. Negative 2 times 1 would give you negative 2, and then you add down the column and you get 0. So then these numbers down here, the 3, 4, 1, and 0, those are your coefficients and then remainder. So the last one's always the remainder, and the 3 in front of it are going to be the coefficients. And then what you should have for the degree is 1 less than the degree of your dividend that you started out with, because your divisor was degree 1. So you'd be subtracting 1 from the degree since you're dividing by something of degree 1. So this should be 3x squared plus 4x plus 1, 0 remainder. And yeah, that's exactly what we end up with here. All right, well then let's see another one of these. If we're going to divide x cubed minus 7x squared plus 4x plus 12 by x minus 6. So x cubed minus 7x squared plus 4x plus 12, there's that just written with coefficients, right? 1, negative 7, 4, and 12. And then the root of x minus 6 is 6. That's why I've got that over here on the left. So then you drop this 1 down. Right, so there's that 1 drop down. Then 6 times 1 would be 6. We put that right here underneath the negative 7. Add down the column, you get negative 1. Then 6 times negative 1 is negative 6. Add down the column, you get negative 2. And then 6 times negative 2 is negative 12. Add down the column, you get 0. So the answer, it's these coefficients down here. So it's x squared minus x minus 2. There's the answer. Next example is slightly blurry, but it looks like it's still pretty much readable. The thing you got to be careful with, no x squared term. So you got to add 1 in. And notice here, I've got that 0. So there's the 1, the coefficient of x to the 4th. There's the minus 5 for the minus 5x cubed. The 0 is for x squared. Because even though that's not there in the polynomial, you've got to include it with a 0 coefficient. Otherwise, you're going to end up with something that's all kind of thrown off. Then 2x will give you that 2. Negative 1 just gives you a negative 1. And then the root of x plus 1 is negative 1. So bring the 1 down. Then negative 1 times 1 is negative 1. Add down the column, you get negative 6. Negative 6 times negative 1 is positive 6. You add down the column here, you get positive 6. 6 times negative 1 is negative 6. You add down the column, you get negative 4. Negative 4 times negative 1 is positive 4. You add down the column, you get 3. So this time we have a non-zero remainder. And the degree should be 1 less than the dividend. So that means that should be 1x cubed minus 6x squared plus 6x minus 4, and then a remainder of 3. So going over here, x cubed minus 6x squared plus 6x minus 4. And then here's the remainder of 3, right? Remainder divided by the divisor. So since we're dividing by x plus 1, this will be 3 over x plus 1. Then the next thing that starts on this page is the idea of synthetic substitution, where you can use synthetic division to evaluate a function. This is really just another version of the remainder theorem, where then what you do here is to evaluate the function, then you just do synthetic division, figure out what the remainder is, and you go from there. So it's like the remainder theorem, just in the opposite direction, pretty much. So if this is what our function is, and we want to find f of 3 using synthetic substitution, you can do it using synthetic division, where then the 4, 8, 5, 2 are coming out of this polynomial, and then it's the same thing as dividing by x plus 3, right? So then we'd have this root of x plus 3 that's negative 3, and then you do the synthetic division, right? You bring down the 4, then 4 times negative 3 is negative 12, add down, you get negative 20, multiply that by negative 3, you get positive 60, add down, you get 65, multiply that by negative 3, you get negative 195, add down, you get negative 193. So that means the remainder is negative 193, so that's what f of negative 3 is. So that's the remainder theorem, just going in the opposite order of how it went before. And then there's another example of this as well. This is one where you got to be careful again, because f of x doesn't have an x squared term. So when I write out the coefficients, I've got 1, negative 3, 0 to cover that x squared term that's missing, then 1, then 6. And then if you do the synthetic division, so you bring down the 1, then 1 times 2 is 2, you add down, you get negative 1, times 2 is negative 2, you add down, you get negative 2, and so forth. Eventually here you get a remainder of 0. So if the remainder is 0, that means that f of 2 is also 0. And that would mean that x minus 2 evenly divides that polynomial that we started with, x to the 4th minus 3x cubed plus x plus 6. So that means that 2 is a 0 of that polynomial, which we might need that sort of concept a little bit later when we're factoring big polynomials. This is one way to get started. So that's kind of why I wanted to throw this thing in here. So you could use synthetic division to figure out if a given value is a 0 or a root of a polynomial. Because if the remainder is 0, then it's going to be a 0 of the polynomial. If the remainder is not 0, if it's anything else, then it's not going to be a 0 of the polynomial. So this first one is for a 0 of this polynomial. Well, we can write out that polynomial with its coefficients. And then we've got the 4 over here, and we can do synthetic division, right? Bring down the 1, multiply by 4. 1 times 4 is 4. You add down to get 0, and so forth, right? Another 0 here, negative 8, and eventually you end up with 0 as the remainder. So since the remainder is 0, then that's a yes. 4 is a 0 of the polynomial. So is it a 0 of the polynomial? All you're really looking at is the remainder going to be 0 or is it going to be something else? So here it's 0. In number 2, it's something else. I wanted to get 2 and 3 up here at once. I can't really do it. 3 is too big. Okay. Well, with 2, do the same sort of thing. Where I can rewrite the polynomial just with its coefficients, and we can do the synthetic division. Here, you eventually get a remainder of negative 66, which is not 0. So since that's not 0, no, that's not a 0 of the polynomial. Negative 6 is not. All right, 3, this one's kind of interesting because you've got that square root and you think, oh, this is going to be really ugly. It's actually not that bad. But the other thing that you have to watch out for is this polynomial doesn't have any terms of odd degree. So you've got to add in coefficients of 0 to cover those. Right? You have a 0x to the 5th, a 0x cubed, and a 0x. So look at what I've got here. I've got 2, 0, negative 10, 0, negative 15, 0, negative 91. And all those zeros are to cover for those terms that aren't in this polynomial. But then you could do synthetic division still, or you'd bring down the 2, and then 2 times negative, or 2 times radical 7 is 2 radical 7. You add down, you get 2 radical 7. Then you multiply that by radical 7. Radical 7 times radical 7 is 7. So that's really 7 times 2, which is 14. You add down, you get 4. 4 times radical 7 is 4 radical 7. You add down, that's just 4 radical 7. But then you multiply that by radical 7. Radical 7 times radical 7 is 7. And then 7 times 4 is 28, right? You add down, you get 13. 13 radical 7, when you multiply, you add down, you get 13 radical 7. You multiply that by radical 7. That's 7 times 13, which is 91. Add down, you get 0. So this one actually does work. You get a remainder of 0. So yes, radical 7 is going to be a 0 of that polynomial. So this one's a little bit different just because of how the algebra works, how you've got those square roots in there. But occasionally those are going to happen, right? You don't have to have zeros or roots of a polynomial that are always integers. You can have them be roots. So every once in a while you do get this sort of thing going on. For the examples on this page, we're going to take some larger polynomials than we've had before. So we're going to take ones that are cubic and we're going to factor them all the way. Because if we know that 5 is a 0 of this polynomial, we should be able to get the other ones because we're going to be left with a quadratic. And either we'll be able to factor that or we can use the quadratic formula and that should do it. So, synthetic division here where we're going to divide x cubed minus 3x squared minus 21x plus 55 really by x minus 5. So you go through and do it, you get the remainder of 0, which we know we're supposed to, right? Because it said that 5 is a 0. But here the remainder is not the important thing. Here the rest of this is. So what we're getting is that that original polynomial divided by x minus 5 must be x squared plus 2x minus 11. Or to rewrite that, x cubed minus 3x squared minus 21x plus 55 must be equal to x minus 5 times x squared plus 2x minus 11. And then we just have to find the zeros of this, right? Because we can't factor x minus 5 any farther. X squared plus 2x minus 11 does not factor, so we're going to have to use the quadratic formula, or I guess if you wanted to complete the square, you could do that too. But if x squared plus 2x minus 11 is 0, using the quadratic formula, you'd end up here just subbing everything in. So that ultimately ends up being, if I go over here, negative 2 plus or minus radical 48 over 2. But you can rewrite the radical 48 because 48 is 16 times 3. So square root of 16 is 4. Negative 2 plus or minus 4 radical 3 over 2. And then I broke this up just to kind of illustrate the cancellation a little bit better. So negative 2 over 2 is negative 1. And then 4 radical 3 over 2 is 2 radical 3. So those are the other two zeros. Negative 1 plus 2 radical 3 and negative 1 minus 2 radical 3. So that's the idea. What you're left with after you divide, if that's a quadratic, if that's got roots, we already know how to get them. So that's also what example number 2 is. Right? We're starting off with this cubic, and then what we're going to do is we're going to try to factor the whole thing, but we know that negative 3 is a 0. So we'll do the synthetic division. We're going to get the remainder of 0 like we're supposed to, and then the quotient is 2x squared plus 5x minus 7. Right? So then that would mean that 2x cubed plus 11x squared plus 8x minus 21 is x plus 3 times 2x squared plus 5x minus 7. That happens to factor. So down here, I've got that 2x squared plus 5x minus 7 is equal to 2x plus 7 times x minus 1. So then that means that the original polynomial that we started out with would be equal to x plus 3 times 2x plus 7 times x minus 1. So there's the version of it entirely factored out. Last but not least, going back to long division, you can have long division where your divisor is a little more complicated. So like in this one, the leading coefficient isn't a 1. That's okay. We can have that. You can also have higher degree with the divisor. It might be missing terms. So like it says here, you might have to add in terms of the coefficient of 0 into the divisor as well as the dividend. Sure, if you were dividing by x squared plus 3, you have to rewrite it as x squared plus 0x plus 3, and we're going to see that in the second example. But here, it basically works the same way it did before. Right? The dividend that we've got, it's got an x to the 4th x cubed, x squared, x constant, so we don't have to add in any terms of the coefficient of 0. And then it's still the same idea where you have to figure out, well, what do you have to multiply 5x by in order to get 20x to the 4th? Well, you need a 4 times 5 to get the 20. You need an x cubed times x to get the x to the 4th. So it's 4x cubed. And 4x cubed times 5x will give you 20x to the 4th. 4x cubed times 1 is 4x cubed. So you have 20x to the 4th minus 4x cubed. You got to subtract that out. You end up with 10x cubed. You bring down the next term, the minus 2x squared. You say, all right, what do you need to multiply 5x by to get 10x cubed? 2x squared, right? Because 2 times 5 gives you the 10. X squared times x will give you the x cubed. So there's the 10x cubed. And then 2x squared times 1 is 2x squared. You subtract that line out. Well, you're left with nothing, right? Both of these subtract out entirely. So 0x squared plus 15x. And then, well, what do you multiply 5x by to get 0x squared? 0x. That'll give you 0x squared. So you get 0x squared, and then plus a 0x, and 0x times 1 is 0x. Subtract that out. All you're going to be left with is 15x, and then you bring down that minus 2. So 3 times 5x will give you that 15x, and then 3 times 1 is 3, so you get 15x minus 3. Subtract that out. You end up with negative 2 plus 3, which is 1, so we got a remainder of 1. All right, so then the final answer, you don't need to write the 0x into the final answer. I suppose you could if you wanted to, but it's unnecessary. So we're going to end up with 4x cubed plus 2x squared plus 3, and then plus the remainder of 1 over the divisor of 5x minus 1. Next example, this is one where you've got to be careful with the divisor a little bit because that does have a term with a coefficient of 0. The dividend doesn't, right? The dividend is good to go as it is, but here there's no x term, so you've got to rewrite the divisor, and you can see it over here. I've got it in red, the plus 0x. You've got to put that in there, otherwise you're going to end up with something that just gets off track a little. All right, well then we need to figure out, we need to multiply x squared by to get 4x to the fourth. So 4 to get the coefficient right, and then x squared, because x squared times x squared gives you the x to the fourth. So 4x squared multiplied by this trinomial here, you'd get 4x to the fourth plus 0x cubed plus 12x squared. You subtract that off, you get 7x cubed minus 5x squared, then you bring down the 21x, then 7x times x squared will give you 7x cubed. So multiplying that out, you get 7x cubed plus 0x squared plus 21x. Subtract that out, minus 5x squared plus 0x, then bring down the minus 15. Minus 5 times x squared give you minus 5x squared. So then there's that minus 5 up there. You multiply that by that whole trinomial, you get minus 5x squared plus 0x, and then minus 5 times 3, which is minus 15. You subtract out that line, everything's going to subtract out. You get a remainder of 0. So the answer is just going to be our quotient, 4x squared plus 7x minus 5. Then the last example, this one's nice and short, but I wanted to put this in here just to point out that you can have coefficients that aren't integers, just because we haven't really had that when we've been dividing. So here, you've got to be careful with this dividend, right? There's no x term. You got to put in that plus 0x to get everything to work out correctly. But then we say, well, what do you need to multiply 3x by to get x squared? Well, we say, I know we need an x because x times x will give us the x squared. But we need to get a coefficient of 1. So what times 3 is going to give you 1? 1/3. Right, 1/3 times 3 is going to give you 1. And that's the unusual thing with this one, where that's not something that we've had happen before, where we have a fraction as a coefficient, but you can have it. Right? It's just everything else happily worked out better than that, but you can have it. So I wanted to get an example in here where that happens. So we have 1/3 x times 3x would give us x squared, but then 1/3 x times 9 is 3x. So you have x squared minus 3x, got to subtract that out. And so then we end up with 3x, and then bring down the 5. And so 1 times 3x will give you the 3x, and then 1 times negative 9 will give you negative 9, so 3x minus 9. Subtract off that line, you get 5 plus 9, which is 14, so we got a remainder of 14. So that means the final answer would be 1/3 x plus 1, so our quotient plus the remainder over the divisor, so plus 14 over 3x minus 9.